Hello, my name is Mel, and this following presentation will offer an in-depth look at optical fibre communications cabling, covering fundamentals, cable structures, functionality, protocols, security concerns, and future trends. We will explore both technical and practical aspects essential for understanding this technology. We will begin by examining the fundamentals of optical fibre communication, then discuss cable structures, working principles, and installation methods. Next, we will review protocols, network topology, security aspects, and conclude with challenges and future directions of this technology. Understanding optical fibre communication starts with the basic principles of light transmission. We will also consider its advantages over traditional copper cables and trace its historical evolution to appreciate how this technology has developed. Optical fibre uses light to transmit data through total internal reflection within a core surrounded by cladding. This process enables high-speed, low-loss data transfer over long distances. Optical fibre offers greater bandwidth, immunity to electromagnetic interference, longer transmission distances, and lightweight compared to copper cables, making them ideal for modern communication needs. Optical fibre technology began in the 1960s with early experimental fibres rapidly advancing through improvements in materials and fabrication techniques to become a cornerstone of global communications. This section covers the fundamental components of optical fibres and the various cable types used in different applications, highlighting their design and functional differences. Optical fibres consist of a core that carries light, cladding with low refractive index to contain the light, and a protective buffer coatings to safeguard the fibre from physical damage. Single-mode fibres allow one light path for long-distance, high-speed transmission, while multi-core fibres support multiple light paths suitable for shorter distances and are cost-effective solutions. Loose tube cables protect fibres by enclosing them loosely in tubes. Tight buffered cables have fibres tightly coated for easily handling, and ribbon cables organise multiple fibres in flat arrays for mass fusion splicing. We'll explore the generation and transmission of optical signals, the roles of transmitters, receivers, amplifiers, and advanced techniques like wavelength division, multiplexing for efficient communication. Data is converted into light via lasers or LEDs, transmitted through optical fibres with minimum loss, ensuring and enabling high-speed communication over long distances. Transmitters convert electrical data to light signals. Receivers detect and convert light back to electrical signals. Amplifiers boost optical signals to extend transmission distances without electrical regeneration. WDM enables multiple data channels to be transmitted simultaneously, which is wavelength division multiplying, just so I know what it is, on different light wavelengths, multiplying fibre capacity and optimizing bandwidth utilization. Proper installation, splicing and testing are critical for performance. This section discusses best practices for cable handling, splicing methods and tools used to validate fibre integrity. Installation must minimize bending, tension, and environmental exposure to prevent damage. Proper routing, securing, and protection techniques ensure long-term performance. Fusion splicing permanently joins fibres by melting ends together for low loss, while mechanical splicing aligns fibres along a side for quicker temporary connections. And I would do fusion rather than mechanical, but it is what it is. Optical time domain reflectometers, or OTDR, detect fault and measure fibre lengths. Light sources and power meters access signal strength to verify cable performance and quality. Okay? Effective communication requires standardized protocols. We will review key protocols like SONET and SDH, Ethernet over fibre, and emerging standards enabling next generation networks. SONET, or Synchronous Optical Network, and SDH, Synchronous Digital Hierarchy, are standardized protocols that facilitate high-speed synchronized communication across optical networks. Ethernet standards over fibre support varying speeds from 1 gigabit per second to 100 gigabit per second, widely used in enterprise and data center environments for fast and reliable data transfers. PONs, or passive optical networks, and DWDM, or dense wavelength multiplexing, significantly increases fibre capacity by multiplexing multiple net wavelengths. We will look at common optical network topologies and applications, from point-to-point links to complex deployments like FTTX and data center infrastructures. Point-to-point topology connects two endpoints directly, while ring topology forms a closed loop, offering resilience and redundancy in optical networks. FTTX topologies deliver fibre closer to end users, FTTH home, FTTB building, and FTTC curb, enabling high-speed broadband access in various environments. Optical fibres power high-speed data interconnects inside data center and support long-haul telecommunications. Security is paramount in optical fibre systems. This section addresses physical security, eavesdropping risks, and encryption methods to protect data integrity and privacy. Protecting fibre infrastructure from tampering and physical damage is critical to maintaining secure and reliable communication channels. Though difficult, fibre tapping is possible. Detection techniques and proactive measures help mitigate the risk of unauthorized data interception. Encrypting data at both the physical layer and high protocol layers ensures confidentiality and integrity during transmission over optical networks. We conclude by highlighting current challenges such as installation complexities, scaling demands, and explore future innovations integrating optical fibre with emerging technologies. Complex installation processes and delicate fibre handling required skilled personnel and advanced tools to ensure network reliability and performance. Meeting growing bandwidth demands involve developing new technologies like advanced modulation, improved multiplexing, and higher capacity fibres. Future optical networks will increasingly integrate with technologies such as 5G, and is already starting to, IoT, which is Internet of Things, and cloud computing driving innovation and expanding capabilities. And look, honestly, sorry, it's already doing that, okay? Optical fibre communication is a transformative technology ensuring high-speed, secure data transmission worldwide. Understanding its principal components and protocols is essential as it continues to evolve and support future digital infrastructure. Thank you for your time.